Hey class, we just finished talking about the wavelength of matter, wavelength of particles, seeing that particles can act both as matter and waves, and we focused on electrons, which we're going to focus on again today. Where do electrons exist? In atomic energy levels. And so we're going to dive deeper into that, and to make more sense of how we can apply what we know in very simple situations, such as an hydrogen atom. So we are looking at the equations that are in our data booklet. This is true. That's the energy of a photon. This E max, which is like kinetic energy max, is something we did with photoelectric effect. And so that's check. Actually, that's check. And then the E equals 13.6 divided by n squared EV. That's something we're going to do today. And then we're also going to do MVR equals NH over 2 pi, which is really, you won't see many problems with this. This doesn't exist in math problems. You'll see them in conceptual problems. You'll see what is the significance of this. And that's all we're doing today, is those two, in this video, is these two equations. You'll notice that I don't see the wavelength of an electron or of a particle. You're going to have to remember that. So, right, that's always going to be lambda is equal to h over p. I'm going to have to remember that. Okay, since we're talking about the Bohr model, we want to go back to what we know already about it. And that is that we know photons get absorbed or emit depending on if an electron is being excited or going down energy levels. So let's do this warm-up. It starts with the frequency of the absorbed photon excites an electron from the ground state, n equals 1 to the third energy level. The words I'm focusing on are, well, I need to find the frequency. It's an absorbed photon, and it's going from the n equals 1 to the n equals 3 state. It already says it's getting excited, so it kind of gives you some hints on the direction, because it's going from 1 to 3, and we know it's absorption. We also know that this photon that came in has a specific energy, E equals hf, and that is going to be equal to the change in the energy level. So go ahead and begin solving this problem. You have all the information, at least for, let's say, part A. I'm going to pause this video, and I'll show you the answer in a little bit. All right, we're back, and I want to emphasize we're looking at this chart in electron volts, EVs. So you're going to have to identify that and remember to convert EV to joules if you want to use the Planck constant that uses joules, which that's what they provide you. So that's what you'll need to use. So I've got a change in energy of 1.9344 times 10 to the negative 18th joules. If you ended up with 12.09, that just means you need to convert it to joules. And then after that, I know my change in energy is equal to HF, given the H that is in my data booklet of 6.63 times 10 to the negative 34, we'll end up with a specific frequency, 2.92 times 10 to the 15th. The next part is, as the electron drops back to the ground state, draw all possible electron transition as it returns. So you need to remind yourself that it won't only go all the way down, although that is one of the paths it can take. It can also go down to n equals 2 and then go down to n equals 1. So there's 3 different possible transitions from 3 to 1. Now, we're going to take this understanding of how of energy levels for atoms, and we're going to dive a little bit deeper. So in order to do that, though, there's a couple processes I need to take. The first we're going to talk about is just Bohr's postulates, kind of briefly. And this is what we already know related to atomic energy levels of electrons, is that they stay in stationary states. We didn't actually understand why. We're going to dive deeper into why right now. And that the electrons jump from one orbit to another by emitting or absorbing electromagnetic waves. So those two things we actually at least already know exist, but we haven't explained why. That shows up here in this example where, and the warm-up that we did, remembering that this is delta E equals HV. At some point in time, they use V for F. It's the same thing. But the third one is something that helped give Bohr an understanding of energy levels being in quantized states, and quantized states meaning it's not a continuous orbit like the way planets orbit the sun, but they exist in specific radii. And in this case, we learned that the angular momentum, this is kind of weird, but angular momentum of an electron is quantized into multiples of h over 2 pi. So like 1h over 2 pi, 2h over 2 pi, 3h over 2 pi. Recognizing that angular momentum, again, this is where IB made a mistake, but they threw this in here anyways, so you do need to just kind of know the concept, and then I'll guide you through a little bit of the math, is that angular momentum is equal to mvr, and it's given the symbol L, again, something weird, the same way that regular momentum is P, there's probably a Latin word for it. In order to get to this understanding that there are quantized energy states, we need to dive deeper into how can we use the wavelength of electrons while they're in orbit. So, okay, electrons act as waves. That's what we did, right before this. And then we're going to take into consideration how an electron could exist in an orbit, and it has to do with standing waves. Remember standing waves? Let's do a quick refresher. And it's mostly B, C, and D, when we had like a string moving up and down between 2 points, and it existed, it kind of harmonized and created different harmonics depending on this, like the speed of the string and all of that. Well, in this case, we're really just focusing on electrons and their wavelength and the length of the string. You see in part A, we're actually going to try to think of an electron going back and forth. It's called an electron in a box. And this is a one-dimensional simple harmonic motion. But if we twist it, we end up with it going in a circular path back and forth inside of an orbit. Remember that in standing waves, if something had a constant wavelength, it could exist in different harmonics if we extended the tube. So like it's its first, well, this is actually technically its second harmonic, but we're going to see how this will, in a circle, this is our first harmonic. And then if we extend the length of the tube or length of the string, we get a second harmonic and then a third harmonic and a fourth harmonic. Now, it's important to see that unlike in standing waves, we needed the beginning and the end to be kind of going in the same direction, because these are all circumferences inside of a circle. So they need to kind of connect and continue their standing wave pattern inside of their orbitals. So the first orbital, which we consider like the ground state, is going to be like this orbital. And it goes around and then reconnects. The second orbital starts at the beginning, going up, it goes around, and then its second standing wave pattern exists here. And let's say I started at this end, right? Let's say it goes up and then down, and then up and then down, and then it restarts so that this section and this section can reform the standing wave. So this is how we consider electrons to act as standing waves in circular orbits, and that's how we identify electrons to be in quantized energy levels. So let's try to dig deeper with this. Well, this is pi r, right? That's our first, 2 pi r is our first circumference, and that equals 1 lambda. The second one is, 2 pi and then r2, because it's a further distance away from the center, and this is equal to 2 lambda. And we keep on doing this. That's 3 lambda, and 2 pi r4 is equal to 4 lambda. Because you'll notice that the wavelengths are all the same. Now this provides us a pattern. If we divided 2 over to the right side, we end up with a pi r of like some n energy level to be equal to, it's 1 lambda over 2, 2 lambda over 2, 3 lambda over 2. So it's going to be n lambda over 2, where n are our energy levels right? Which is like we consider ground state to be 1, 2, 3. There's no 4 because that wouldn't make sense. And lambda is our de Broglie wavelength of our electron that's orbiting. Now, to kind of give a expanded example of these standing waves, we have, let's move this down. We don't need to look at this yet. We have our 1, 2, 3 energy levels there, and here are our different ones. It's kind of hard to see which one's which, but how about this? We can play a small game. Try to guess which energy level each of them are. So the first one is n equals 3, and I drew one wavelength. I did it from trough to trough, right? Because the next wavelength would be trough to trough, and then the next wavelength would be trough to trough. And I could do that all the way through. You'll notice, hey, if there's 3 crests, right, that means there must be 3 wavelengths. So n equals 3, n equals 4, n equals 5, n equals 6. And these are our examples of some examples of the where we get that whole SPDF. But again, it gets more complex than that, so we just kind of stop and say, I'm partially lying to you, and we move forward. But all that we've learned so far is that there are quantized energy levels, and we've started to dig a little deeper in that. And we're also going to show how angular momentum is quantized right here. Actually, I do need to move it up then. But this is kind of silly. This doesn't take us anywhere. But IB might ask you to show how you do this. So let's just show you how to do it. So we know that our de Broglie wavelength is lambda is equal to h over p. We also know that p is equal to mv. And then we just showed that, what is it, pi r? Pi r equals n lambda over 2. Pi r and pi rn equals n lambda over 2. So we're really just kind of plugging things in. We know lambda is equal to h over p, and p equals mv. So let's just kind of plug both of those in, right? So I'm going to take this section, and then I'm going to take mv, and I'm going to move it in to p. And then I'm going to take all of that and plug it into my lambda. So h over mv is going into lambda. We're in red. So I have pi r is equal to n h over 2 mv. And then I'm going to focus on the parts that give me angular momentum, which is mv and r. And I'm going to write this as mvr is equal to nh over 2 pi. Hey, and we got it. We have angular momentum is equal to the energy level times h over 2 pi, meaning it's quantized. This becomes important later. Not something you really need to know, but you might need to know this derivation. So the next important part, and one where actually has a equation in the data booklet, energy is equal to 13.6 over n squared eV. This is the amount of energy at each energy level of hydrogen. Only hydrogen. I'm not going to show you this derivation. Well, I'm not going to do the derivation. I'm going to show you a synopsis of the derivation, and it's going to kind of laugh. We're both going to kind of laugh. Here we go. This is it. So it's kind of cool. So I highly suggest that you kind of just at least look at it, and it's just algebra, so you can easily work through it. We start with centrifugal force is equal to electric force of a hydrogen atom. So knowing mv squared over r is centrifugal force, and then the electric force is ke squared over r, because there's only one proton and one electron, and that's what allows us to do this. Beyond hydrogen, it gets much more complex, and we start needing much different types of math, not just straight algebra. Okay, so again, they do this. They kind of rearrange to where, hey, look, we have mvr, or the square of mvr right here. We just came up with mvr is equal to nh over 2 pi. They plug that in, and they end up with r is proportional to n squared, because everything inside of this little purple circle is a constant. They continue with that, and they say, well, what about the energy, the total energy of these orbits? And they look at Ek and Ep and make some references to K, K is equal to 1 over 4 pi epsilon naught. Again, recognizing that the charge is 1 proton and 1 electron, so it's really only a hydrogen atom. going throwback to orbital energy, saying that EK is equal to the negative half of the potential energy, and then plug, and then we end up with an equation, a total energy equation, where these blue are all constants, and you find that the energy is proportional to 1 over n squared. So the energy of an electron in orbit. And that's where we end up, if we plugged in all those constants, we'd end up with just a value of negative 13.6 eV. So all of those blue constants, let's make that blue. All those blue constants, is just 13.6 in electron volts. And that's where the equation comes from that we can use to determine the energy levels of a hydrogen atom, or the energy of the energy levels of a hydrogen atom, but only a hydrogen atom. And that's why we did this problem in the beginning, is because these are, let's do it in yellow, this is the energy level of n equals 1, the energy level of n equals 2, 3, 4. Go ahead and plug in 13.6 divided by 1, 13.6 divided by, or rather 1 squared, 13.6 divided by 2 squared, 13.6 divided by 3 squared. It shows up as these values. So let's do this, well, still called a Giro problem here. Let's do this Giro problem where we want to show that the wavelength of an emitted photon when an electron jumps from the 4th orbit to the 2nd is 486 nanometers, recognizing that we have nanometers. We'll need to use this change in E. Well, I guess they don't tell you, sorry, this E is equal to negative 13.6 divided by n squared, and recognizing that it's EV. So don't use this chart yet. We're going to use that chart just to check our work. So we'll need, again, do E final minus E initial, but in this time we're going to actually solve for E final and E initial using our 13.6 divided by n squared. So I get negative 13.6 divided by, well, it's my final orbit, and I'm going my 4th to my 2nd, so I need to go 2 squared minus negative 13.6 divided by 4 squared. This gives me negative 2.55 eV. But this is our change in energy, and I know that's going to be hc over lambda. But we have a problem here, is that we're in electron volts. So first we actually need to convert that. So we know that this is 1.6 times 10 to the negative 19th joules per electron volt. And that gives me a value that's 4.08 times 10 to the negative 19th eV. Joules. Right, and this is equal to hc over lambda, where since h is in joules, we can do this. And I can, I want to solve for lambda, so lambda is equal to, well, h, 6.63 times 10 to the negative 34, times c, 3 times 10 to the 8, divided by my energy, 4.08 times 10 to the negative 19th. And if I were to plug this in, I get 4.88 times 10 to the negative 7, which is that's close enough. 486 nanometers. And if we're going from 4 to 2, we get 486 nanometers. So we've confirmed to the, within rounding, because 13.6 is most likely rounded, this question. That's all we have. So this is, again, kind of some weird, dense stuff, but really the focus is recognizing that our understanding of energy levels inside of atoms are based off of electrons moving back and forth or in a circle based off a standing wave pattern. That, of course, gets more complex with more protons and electrons, but if we just go to a simple hydrogen atom and use the wavelength of the electron that we know, lambda is equal to h over p, we end up with some derivations that show us the angular momentum is quantized, the radius is quantized, and the total energy of the energy level of the electron is quantized and proportional to, in this case, 1 over n squared, which is in our data booklet. That's it. That is today's finish of the lesson. Good work, and see you in class.